So she's not coming, is it? Oh, okay. Oh, I haven't finished marking my attendance. Okay. Sorry, Emily is not coming, is it? Oh. Sorry. Jing Kai is here. Is Jing Kai here? Do you see Jing Kai? Do you see Jing Kai? Yes. So he's still there. Okay, sorry. Come. Let's come. Let's look at the lecture notes now. Okay, so if I'm not wrong, right, we stopped somewhere at a checkpoint. So do you still remember the page number of that checkpoint? Okay, so 14. Okay, before I resume the lesson, do you have any particular question to clarify with me? Let's say if I say something that confuses you over the past few days, when you look at it, you're still confused. Is there anything that you want me to clarify? Okay. So usually after I teach you, I will go back and do reflection. But it seems like students don't really do that. Okay. Yeah. Okay. So let's look at this. All right. So question 1A, we have talked about iron 2 versus iron 3 as an oxidizing agent. So we know that in the half equations, right, oxidizing agent appear on the left side or the right side. Do you still remember? Oxidizing agent, usually they are found on the left side or the right side. The left side. So reducing agent are on the right side. Okay, so our reducing agent, so on the right side, and you must consider reverse of that reaction. Okay, so if you look at this, right, it's an R cube. Reducing agent on the right side, and it goes the reverse way, which is the oxidation process. Okay, R cube. All right, so we'll remember this in this way. So between these two, right, we know that iron 3 and iron 2 must be found on the left side. So there are 3 possibilities involving iron 2 and iron 3. So among the iron 2, there's only one possibility, so no argument. Iron 2 to iron 0, negative 0.44. But if you look at iron 3, there are 2 possibilities. One is minus 0.04, that is becoming iron 0. Then the second alternative is iron 3 accepting only 1 electron to become iron 2. So that is a positive 0.77. So between these 2 possibilities, okay, I highlighted to you that it must be the one that is more positive will be taken as the reference. Okay, so that's why we cancel this away. Because among 2 iron 3 here, this is the one that is more positive. So we'll use this as a reference for comparison. All right, Ken? Clear? So similarly, if you talk about chromium 2 as a reducing agent, so because it's the reducing agent, it will appear on the right side of your equation. All right, so if it's appearing on the right side, then you should be comparing how negative it is. The more negative it is, it will be a stronger reducing agent. Okay, so what's your conclusion? What's your conclusion? So the half equation that you can have, right, will be chromium 2. So among the equations that you can obtain from data booklet, this is the only chromium 2 that appears on the right side. Okay, so these are not relevant because they are on the wrong side. Okay, so this is negative 0.41. So if you look at iron 2, which is on the left side, this is the only one. Only iron 2 on the right side. Okay, so this one is a positive 0.77 volt. Okay, so basically you just need to compare this versus this. So which one is more negative? Chromium 2 plus. So chromium 2 plus being the more negative will be a stronger reducing agent as a result. Ken, so far so good? All right, so you need to know how to select the half equations from your data booklet. So for this topic, right, selection of half equation is a skill that is very important. So in your inorganic QA, deciphering how the observation matches with the QA notes, also an important skill. Yeah, okay. So let's try to work on that. All right, so if you look at B part 1, strongest oxidizing agent. So if I'm talking about strongest oxidizing agent, then I should look for this oxidizing agent on the left side or the right side. Yeah, left side. Okay, so it must be a left side, and I must have a most positive E naught value. Okay, so this E naught here, I'm referring to the standard electrode potential. The one with the most positive E naught for the reactant on the left side will be the strongest oxidizing agent. So what's your answer? What's your answer? If you don't want to tell me, can you tell your neighbor what's the answer? Because you really must practice selecting it. Don't wait for my answer. You must practice the thinking skill. So what's the answer? Fe3 plus, are you sure? The most positive E naught leh. If you have your data booklet with you, right? If you have your data booklet with you, then you should be looking at table 4A. Okay, if not, right, you can refer to the last 2 pages of the handout. So what is the most positive E naught? Which element? Tell your friend at the very least. See whether you can get the same answer. So what's the answer? Oh, can I have the time practice paper? No, it's okay. So it's time practice. I will return it to you tomorrow. Yeah, I'll give you some feedback first. Who else? Can you pass it to me first? I'll give you feedback, then you do the corrections. Yeah, I know. It's okay. So what's the answer? Fluorine. Okay, so do you manage to get fluorine? So among all the elements on the left side, fluorine is the one that gives you the most positive electrode potential. Okay, then how about reducing agent? So if it's reducing agent RL, then you should be looking at species on the right side. Okay, so since you are looking at the reverse direction, then you should be talking about the more negative it is. All right, in the reverse direction. So the E naught value should be most negative. So what do you find out? Reactants on the right side having the most negative E naught. Who is it? Lithium. Do you find lithium? Yeah, so that's how you do it. So you must know which side are you looking at. Okay, so on left side, most positive. On right side, most negative. Can? All right, the reverse direction. Okay, so let's move on. Is it okay? All right, so let's look at the next one, standard cell potential. All right, so previously we have talked about the electrode potential, standard electrode potential. Now is standard cell potential. So please take note, typically in an A-level question, they will not spell standard cell potential. They will just use this as a symbol. Okay, so in an A-level question, they will just ask you calculate E naught cell. So you must know is referring to the potential difference between two half cell measured at standard condition. Okay, and I hope you still remember what is the meaning of standard condition. Temperature, pressure, 1 bar for gases if it's involved, and all aqueous ions, 1 mole per dm cube. Okay, so can you also make this change here? A-level don't use this term. A-level uses standard electrode potentials. Okay, A-level only use standard electrode potential, but you must know that we are referring to reduction potential. Can? Okay, so if this is the mathematical representation on how we can calculate our E naught cell. Okay, so we have the cathode. So reduction is where cathode takes place. So cathode is where reduction takes place. Yep. Then anode is where oxidation takes place. Okay, so for those in JH, right, please associate this whole thing as your E naught oxidation. Okay, you have to change that notation. Can just switch a little bit. Okay, so minus E naught, right, is actually your E naught oxidation. Okay, so what is the difference between the E naught cell and the E naught that we have learned so far? This one. What is this? These are your standard electrode potential. So it's not a cell, there's no subscript cell here, it's just referring to the half cell. Okay, so essentially, right, it is always measured against your SHE. Okay, so essentially it is your E naught, tendency for it to undergo reduction, minus away your E naught of SHE, standard hydrogen electrode. And this is by default equal to 0 under standard condition. Okay, so that's why, right, essentially these two are equal because this is 0, right? This is 0. So by right, standard electrode potential, even though it's always measured against the SHE, it will not appear in the expression because it's 0. Okay, no effect on the value. But it's also a potential difference. Can? All right, so far so good. Okay, so if you are okay with this, right, then we'll look at this part. Okay, so for those who are learning physics, right, please take note, electromotive force is what you use in physics, EMF. Okay, for chemistry, we use the term E naught cell. All right, so that should be the difference. So please know that we are referring to the same thing, even though it's a different context. Okay, so let's look at this. Using the data booklet on page 16, right? Okay, using the data booklet, okay, these are the two half cells. So just now, you won't ask me, how do I know which half cell is the anode, which half cell is the cathode? Okay, so this is where we are going to learn to identify that. Okay, please be reminded what is a half cell. Right, so half cell is an equilibrium of a particular element at two different oxidation number. Okay, it must have a particular element at two different oxidation number. Very important. That is considered as a half cell. Okay, and I need to remind you, it need not be in the elemental form. It need not be the elemental form. So for example, the first example, right? This sulfur here exists in a compound. Okay, so the oxygen here is the one that is in equilibrium with the different oxidation number. Then manganese and Mn2 plus, your lead-4 dioxide and your lead-2 plus. Okay, so they need not exist in elemental form. Okay, they can appear as a compound. So it's very important for you to recognize which one is it that exists in the two form. Okay, I hope you know that the oxidation number of oxygen here is -1, while the oxidation number of oxygen here is -2. You need to go and recap how to calculate oxidation number. Okay, this is your prior knowledge. Actually, I'm wrong here. It's the oxygen here. Okay, never mind, that is too complicated. Okay, all right, so let's move on. Okay, so let's look at this. So between the two electrode potential, notice that copper 2 is the one that is more positive. Okay, so I need you to recognize that the electrode, the half cell involving copper 2, copper 0 is having a more positive E naught value. Okay, so this means that by default, it will be the one forming the cathode. It will become the cathode because it has a greater tendency to undergo reduction, right? So therefore, it will automatically become the cathode. So in other words, if copper 2 copper half cell is the cathode, then zinc 2 plus zinc half cell will be the anode. It must be a cathode and an anode, right? Cannot be both anode, cannot be both cathode. All right, so one will be cathode, then the other one will naturally be the anode. Okay, so when it's the anode, then you need to see that it will be the reverse process. Okay, then you combine the two half equation, it will give you the overall. All right, so notice also something, right? Please take note. When I look at the two half cell, we use a reversible arrow. Okay, so we are showing the individual half cell. And from the comparison of the standard electrode potential, I can define the direction of reaction. So once I have defined the direction of reaction, I will use a complete arrow. I already know that this is cathode, so I use a complete arrow. So similarly, for the anode, I can use a complete arrow. Then this will represent the overall reaction. Am I clear on this? All right, so do appreciate that. Similar, okay, so let's draw some similarity to what we have learned so far. Similar to enthalpy change of calculation, when the equation is flipped, when my reactant is on the right side, we are talking about the reverse direction. Okay, right? So this means that the sign of the value will also be reversed. So similarly, if my E naught value is A, then if I'm reversing the direction, then it will become a minus A. You need to put a negative sign in front. Okay, but please take note, enthalpy change is affected by the number of moles of reaction taking place. E naught is not. Okay, all right. So if you look at the example whereby my zinc is oxidized to zinc 2 plus, if I'm having a silver plus reacting with it, there should be 2 moles of silver plus, right, to receive the 2 electrons. Okay, so do appreciate that the tendency of silver plus 1 mole to receive 1 electron versus 2 moles of silver plus receiving 2 electrons is exactly the same. They are the same. Okay, so do not multiply by 2 if there is 2 moles of silver plus. The whole thing is multiplied by 2. So the percentage of conversion is the same. So E not affected. Okay, am I clear on this? Okay, E naught is not affected because the percentage conversion is still the same as before.
Can you repeat when we use the half?
Okay, before we decided which one is the cathode, we use a reversible sign before we can decide. So after we have decided which one is the cathode, which one is the anode, then we use a complete arrow. Yeah. Yes? It's like a POE, position of equilibrium. Yeah. So if I multiply the whole process by 2, right, the percentage of Ag plus converted to Ag is still the same as before. So that's why the E naught value not affected. Pardon? The amount, yeah, but the percentage conversion is the same. This is how much it takes in. It doesn't go, I mean, even if you start with more, right, it doesn't, yeah, because you see, when you multiply the whole thing by 2, the number of moles of electrons also multiply by 2. Yeah, so the tendency to receive that electron is the same as before. Yeah, can? All right, so if not, you just memorize lah. It's different. Okay, so please take note, the negative sign here is to reverse the E naught value. Okay, so do appreciate that the negative sign here is to reverse the E naught value because we are minusing the oxidation process. So that is to reverse the value, the magnitude. Okay. Okay, so the minus sign is to flip the value. Am I clear? Okay, so I move on. So let's look at this. Okay, can we quickly look at checkpoint 3? Okay, so in this case, right, you have to identify your half cell. So you need to draw out select the data booklet. Okay, are you able to select one? Okay, you have to practice that. Don't wait for my answer. Check with your friends. Are you on the right path? Do you report to the GO? Okay. Okay, I'll just give you 30 more seconds. Okay, so sorry, I'll rush a bit. Okay. If you look at the chromium 3 chromium half cell, so where is that relevant half equation? So there's only one of such, so that will be your chromium 3 and your chromium. Okay, so this is not correct one. It's chromium 3 and chromium 0. So this is the one that you are going to choose as a reference. You manage to find that? So the E naught value is a negative 0.74. Okay, these are not relevant. Okay, these are not relevant. Okay, then if you look at the other half cell, which is the iron 2 and iron 0, so between iron 2 and iron 0, this is the only one that is applicable, and that is a negative 0.44. Okay, so this will be irrelevant. Okay, so with this in mind, which one will be the cathode, which one will be the anode? If you look at the value, negative 0.74 versus a negative 0.44, who is the anode? Who is the cathode? Choose the one cathode first. The iron. Okay, because it's a more positive E naught value, right? Do not get confused. Negative sign here means less negative. Other words, more positive. Yeah. Okay, so some of you are confused by the negative sign. Okay, so you have to choose the one that is more positive, less negative. So this will be the cathode. Then of course this will be the anode. Okay, yeah, can see? So if this is the anode, right, then am I able to tell whether statement number 1 is correct or wrong? False. Okay, this will be false because this being the anode, your chromium must be oxidized, right? That's the meaning. Anode must be oxidized. Okay, while iron is oxidized here, no, it's not. It's iron 2 being reduced. Yeah, iron 2 is being reduced. It's not the iron metal. Iron 2 is the one being reduced. Okay, so this is how we make it a correct statement. Yeah, so are you able to calculate that the EMF, or rather the E naught cell? For A-level question, they use this term. Okay, E naught cell plus 0.30. Are you able to calculate that? Can okay, don't need to multiply by anything. Just subtract. Okay, so that will be a negative 0.44 minus 0.74. Okay, so that is your E naught cell. Okay, so this is your cathode, and this is your anode. Okay, so this is your anode. So for anode, you need to put a negative sign to reverse the value because it's in the reverse direction, occurring in the reverse direction. Okay, so how about 3? Iron will be deposited on one of the electrode. Is that true? Is that true? Yes, it's true. Because iron 2 is being reduced to iron 0, so it will be deposited on the electrode. So this is true. Okay, so this is true, true. So false, true, true. Okay, all right. So let's move on. Polarity of the electrode. All right. Okay, so please take note. When you write the equation, when you look at the individual half cell, you can put the reversible arrow. But once you have identified which one is the cathode and anode, okay, notice that I use a full arrow. Okay, so this is how I calculate the E naught cell. And a reminder again, half cell equilibrium. When we have decided cathode and anode, irreversible arrow. Okay, so when you write the overall equation, also irreversible arrow. Okay, so let's look at the next part. Electrode in the oxidation half cell is known as the anode. Okay, So remember, anode always have a negative polarity. Why negative polarity? Because there's electron released. During oxidation, electron is released, source of electron. So by default, it will be a negative polarity. Okay, so on the other hand, if you have a cathode where reduction takes place, then this will be a positive polarity because it will want to attract electrons. Since it's able to attract electrons, it must carry a positive polarity. All right, so opposite charge attracts. Okay, so please take note, this polarity over here is only applicable to electrochemical cell. You should remember there's also an electrolytic cell. Yeah, so electrolytic cell will be the reverse polarity. It will be reverse. So for electrochemical cell, this is how we tell. Okay, then we also talk about the direction of electron flow. Okay, this one should be fine, right? And we you are also introduced in your JH and ox and red cat. Is it introduced? So anode is the oxidation, reduction is the cathode. Yeah, so this definition applies to both electrochemical and electrolytic cell. All right. So while the polarity can be reversed, but this acronym applies to both electrochemical and electrolytic cell. Okay. All right. So let's move on. So let's look at page 18. Okay. So recall that our equilibrium are all reversible processes. Okay. So our reduction potential are in equilibrium with each other. Therefore, any changes in temperature, in pressure, if there's a gas involved, or concentration of the aqueous ions, it will cause the POE to shift. So when the POE is shifted, it will affect the E0 value. Okay, so under standard condition, as quoted from the data booklet, or standard electrode potential of copper 2 to copper 0 will be a positive 0.34. Okay, but then if you make a change to the concentration of the copper 2 plus, this will mean that there will be a shift in POE. Okay, so as you increase the copper 2 plus concentration to 2 mole per dm cube, it will favor the right-hand side in response to the Le Chatelet principle. Okay, so therefore, I will expect the value to become more positive. Okay, so it will become more positive. So I'm going to use the term more positive, less positive, because E0 values comes with positive sign and negative sign. Okay, it will be more explicit if I talk about more positive or less positive. Okay, as a reference. And please take note, I also want you to appreciate that when I use 1 mole per dm cube, there is a phi symbol. Okay, I don't know what is the name of this, chi symbol or phi symbol. Okay, notice that when I change the concentration of copper 2 to 2 mole per dm cube, I omit the phi symbol because it's no longer under standard condition. So that will be omitted. Okay, so as long as there's deviation from the standard condition, you will omit that phi symbol. Okay. All right, so the rest will be Le Chatelet principle. Okay, scenario number 1. Okay, I don't know whether you are comfortable with this. This is what is used in your notes. Or are you more comfortable with this? I'm more comfortable with this. Yeah, so up to you. You are more comfortable with what is given in the notes, you can just continue. If you find that this is more comfortable for you, you can use this approach. Yeah. No difference. It's the same thing. It's just that because of the negative sign, so now I'm referring to whole thing as becoming more positive. Therefore, your E cell more positive. Because of this equation, because of this equation, so cathode is always here in front. So if your cathode is less positive, then of course this will drop. Yeah. So on the other hand, this is the one at the back. So if this becomes more positive, then your E cell will increase. Yeah. Which I thought is clearer to me. Yeah. But if you prefer the notes one, by all means do so. Up to you. Okay. This one I feel is less confusing. Can? Uh, which one? E cell?
Yeah.
Yeah, E cell decreases, or E cell less positive or decreases. Yeah. So you can choose to use the term decrease. It's just that E values comes with a sign. So I will prefer you to talk about it as less positive, more positive, or less negative, more negative, so that I know the direction. Yeah, it's clearer lah, I feel. When you just use the term decreases, increases, it's very confusing. Same thing for enthalpy change. When you talk about enthalpy change, you should be also talking about it being more exothermic, less exothermic, not just increase, decrease. Do you remember what I taught you last year? Gone with the wind. It's the same idea. Okay? Can? Okay, I move on. Can? All right. So if you look at the next part, right? Let's try checkpoint 4. Okay, so for those who are done with copying, right, you can try checkpoint 4 now. If you have any other questions related to other parts, you can clarify with me. Okay, so for this one, you have to choose the correct half cell. Right? So remember the definition of a half cell. It must be an element existing in 2 different oxidation number. Okay, so you must choose the correct half cell. If you choose it wrongly, then you will make a wrong conclusion, of course. Okay, so the half cell on the right side involving your silver electrode and silver plus, that is quite straightforward lah, because that will be your element at two different oxidation states. So this half cell will be a silver plus and a silver. Okay, so you just look for relevant equations that involve both of this. Okay, so this one is quite straightforward. It's a positive 0.8 volt, if I'm not wrong. Yeah, but the left one is more challenging because they are different species. But I need you to recognize that sulfur is the one that exists in two different oxidation states. Are you able to recognize that sulfur is the one that exists in two different oxidation states? So this means that I should look for a half cell having sulfate on the left side, SO2 on the right side. Yeah, so do you manage to find that? Yeah, so that will be your second half cell. Okay, so after you have identified the two half cell, you are supposed to look at which one has a more positive E0 value, standard electrode potential. So which one has a more positive standard electrode potential? Silver. Okay, so if silver is the one that has a more positive E0 value, then this will mean that this is your cathode. So if it's a cathode, then it will be a positive polarity, right? Cathode is the one that receives the electron, so therefore it must be positively charged in order to receive the incoming electron. So the electron flow will be in this direction. Okay, so this will be the source of electron, and this is the anode. Okay, so being the anode, it will be the negative polarity. Okay, so have you made the correct conclusion? Okay, so these are all the workings lah. So this will be what we use as a reference. Okay, so we can calculate the E0 cell coming from the standard electrode potential. So my cathode is here. Then reverse the sign using minus. Then we have our anode. Yeah. Okay. So there's no need for you to multiply by 2 here. That is wrong. Even though there's 2 moles of silver plus involved in reaction, we don't multiply it by 2. Please take note. Okay, so this is wrong if you multiply by 2. Can? Are you able to get the answer? Can, huh? So let's look at part C. Suggest how E cell value will be affected when a few drops of sodium hydroxide is added to your sulfate sulfur dioxide. So how do you think it will be affected? Okay, so looking at this half cell, when I throw in OH minus, what do you think will react? Yeah, the H plus. So you must see this as a base, then it will react the H plus away. So for this particular half cell, H plus will drop. H plus will drop. So if the H plus drop, does it favor? Okay, remember, this is the anode. By right, it should undergo oxidation. Right? So if your H plus drop, does it favor oxidation or does it less favor oxidation? Favor or less favored? It will favor oxidation. Yep. Okay, so oxidation is favored. Anyone who has difficulty seeing that you cannot see why oxidation is favored? As oxidation, right? So the reverse process is the oxidation. So removal of H plus, according to Le Chatelier principle, it will shift to the left to favor the oxidation process more. Okay, in order to partially offset the drop in H plus. Okay, so oxidation is more favored. Therefore, the minus E of your sulfate, SO2, will be more positive. Okay, so notice that I talk about the effect on the half cell first. Okay, we need to talk about the effect on the half cell first, then we associate with E cell. Am I clear on this? Okay, so we are talking about anode and oxidation is favored. So the whole thing becomes more positive. Therefore, E cell more positive. Yeah, so in this case, right, this is what it looks like in your answer. So hydroxide will react with the H plus, so that will cause a disturbance. So this disturbance is your H plus concentration decreases. Remember, the disturbances in responding to the Shackler principle, okay, are concentration, not number of moles. So concentration of H plus drops, position will shift to the left. That means the reverse direction. Okay, so if you shift to the left means favor oxidation. So that value will become more positive, or in this case, is more negative. Because this one is without the negative sign. This is not, this is without the negative sign. So when this decreases or become more negative, then you subtract a more negative value, it will increase your E cell. Do you get it? Yeah. Yeah, the E is always by default reduction potential, standard electrode potential. Can? Huh? Net arrow, if it's full arrow already, there will be no equilibrium. So you have to talk about the half cell first. Okay, so what do you think will be the effect for sodium chloride? Are you more comfortable with this? Okay, never mind. So let's look at part 2. Sodium chloride, what does it do to your silver plus silver half cell? What will happen? It will form your silver chloride PBT. Okay, so the chloride here and Ag plus, having done KSP, I mean, even before you done KSP, you should know that silver chloride is a PBT, right? So that will cause your concentration of silver plus to drop as a result of precipitation of silver chloride. Okay, so when this drop, does it favor the reduction process or less favor? It will favor the reduction process less. So this means that your E value, the reduction value, will become less positive. Right? So this is what is going to happen. Okay, so it's less favored due to the decrease in concentration of silver plus. So it will shift left. Okay, so E value will decrease or become less positive. So this will become less positive as well. Okay, can? So far so good. All right, so just to reiterate, talk about the effect on the half cell first before you relate it to the E cell. Okay? Can I move on? All right, so let's look at page 20. All right, to predict whether a redox reaction will occur, the two chemical species are mixed. Okay, so the two species that you're looking at, right, they must appear on the opposite side of the half equation. Okay, do you know why? Because they must form a redox couple. So one reactant will be the reducing agent, which is on the right side. Then the left side will be the oxidizing agent in order to form a redox couple. So by default, the two species, right, must be found on the opposite side of the half equation. Okay, and please take note, redox reaction may be possible. Therefore, we need to calculate the E cell. All right, so cancel away the term possible. Okay, tell yourself that it may be possible, and the possibility of this reaction, you need to calculate the E naught cell. Okay, so we have gone through the formula of calculating E naught cell. This is what we have done. Okay, and when is the reaction? When is this redox reaction spontaneous? E naught cell must be more than 0. Okay, so we must make reference to more than 0, less than 0, or equal to 0. Okay, very similar to what we have learned for delta G. Okay, but delta G must be negative in order for the reaction to be spontaneous. Okay, so we also do likewise, we compare it with 0 for delta G, but opposite sign. Okay, E naught cell must be positive, while delta G must be negative in order for the reaction to be spontaneous. Okay? Opposite in sign. Okay, so why is it opposite in sign? It's because of the formula later on. Okay, we'll look at it later on. Okay, so let's look at work example 4. Can I ask you to look at part A first? Okay, so one thing I want you to appreciate is, right, we are no longer working with half cell. Okay, notice that the half cell term is not in this question anymore. Okay, what you are working with is just one element in one oxidation number. Okay, iodine, 0, nothing else. Chromium, 3+, nothing else. Okay, these are not half cells. And if we are not working with half cell, how is it going to affect your thinking process? Okay, I need you to appreciate that.
So you select the one that's most negative. If there's more than one decibel reduction, you select the one that's most negative.
For oxidation, yeah, more negative. Now, so you have to be very clear, are you looking at reduction or oxidation? So for oxidation, it's more negative. For reduction, more positive. Okay, so have you finished reading? Yeah, so let's look at what is the difference. So I need you to recognize that there's only iodine. And if you look at your data booklet, iodine only appear on the left side. You'll never see iodine on the right side. Am I right? Okay, so this means that iodine must undergo reduction. Only one direction. Because it only appears on the left side, right? So only one direction. So if iodine can only undergo one direction, this means that your chromium 3 must be oxidized. So if this undergoes reduction, then by default, your chromium 3+ must be oxidized. Okay, and indeed, you are able to find chromium 3+ on the right side of one of the half cell. Yeah, you can find chromium 3+ right on the right side in one of the half equation. Okay, so now you have two species appearing on the opposite side of the equation. So that is the first criteria, right? They must be on the opposite side of the half equation. So iodine on the left side, chromium 3 on the right side. So it satisfies the first criteria. So we need to check the second criteria. When I calculate the E cell, does it become more than 0 or less than 0? So when you calculate the E cell, you discover that A is a negative sign. So even though the two reactants appear on the opposite side, but E cell is less than 0. So it doesn't take place. Okay, so for redox reaction to take place, the two criteria must be satisfied. Opposite side and E naught cell more than 0. Can? Okay, am I clear on this? All right, so if I change the context a little bit, so remember this is your checkpoint 3, and I change it to this. Iodine to iodide half cell versus dichromate to chromium 3 half cell. Right? Now, if I change checkpoint 3, adjust the, using the same phrasing, but I just change the half cell. Now, in this case, will I still arrive at the same conclusion? What's wrong? What's the difference? It will be spontaneous. Okay, so please take note. If I'm working with two half cell, E cell by default is always more than 0. Okay, I reiterate again. The E naught cell you calculated from this two half cell is always more than 0 by default. Yeah. Do you understand why? Because when I look at half cell, I will always choose the half cell with a more positive E0 value to be the cathode. Remember when we do checkpoint 3, what do we do? Or checkpoint 4, what do we do? In checkpoint 3 and checkpoint 4, we are working with half cells, right? In both cases. So how do we decide how reaction takes place? We compare the E0 value. The one with a more positive E0 value will automatically become the cathode. Then the other half cell will be anode. Yeah. So by doing this, right, we ensure that E0 cell is always more than 0. Yeah, when we do that. Can? Yeah, but if you look at this context here, we are not working with half cell. Okay, we are just given iodine and di-di, it must undergo reduction. Okay, and chromium 3, di-di must be oxidized. Yeah, so when we combine, E cell is less than 0. So even though opposite side cannot take place because E cell is less than 0. I need you to appreciate that. Huh? Yeah. 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 So without the half cell, we cannot fit. Yeah, it must be that direction. The direction of reaction is fixed. In other words, it is not half cell. And am I clear on that? Okay, the rest of the work example you can read on your own. Then let's try the, no. Okay, so for part B, right, I need to emphasize. So for part B, the half equations involving your manganate, right? So a lot of you is drilled into the fact that you should choose the one that is more positive, but it's not so for manganate. So for manganate in highly acidified medium, you must recognize that it must be reduced to Mn2+. Okay, you don't choose the one with a more positive E0 value. Okay, it doesn't work for manganate over here. Yeah, only manganate doesn't work. So manganate, right, di-di, you must always remember, is always Mn2+ as a reduced product. Okay, don't consider manganese dioxide unless the question suggests so. Unless the question says so. If not, right, by default, under highly acidified medium, it will be reduced to Mn2+. Okay, can? Okay, so with that, right, you choose that as your half equation. Then oxidation must be iron 2 oxidized to iron 3. So when you calculate, you see that is more than 0. So this is a spontaneous reaction. Okay, and the last one, you can look at it on your own. So do you have any question to clarify with me? Okay, if not, right, then you can try the next checkpoint. Okay, try the next checkpoint.
It's not until we cannot fit. What do you mean?
Oh, because in this case, if I'm working with half cell, between these two half cell, I know that this is the one that is a more positive E0 value.
So we think it will be the cathode.
Yeah, so it will be the cathode. So this means that my dichromate must be the my cathode. Oh no, sorry. The one that is more positive is your dichromate one. Yeah. I mean, you can refer to your data booklet.
Yeah.
Yeah. So between these two, right, this one is more positive. If we are working with half cell, so half cell will be this in equilibrium with this.
Yeah.
So it's a positive 1.33. Whereas another half cell will be the iodine in equilibrium with the iodide. So that is a positive 0.54.
Yeah.
Yeah. So for this one, right, since it's more positive, it will be by default the cathode. Yeah. So it can go in this direction. Then this can go in this direction because iodide is present.
But then for in this case where we are not working with half cells.
Then iodide is not present. Iodide is not present, dichromate is not present. Notice that? Yeah. So if dichromate is not present, right, then I cannot undergo reduction here. You can only undergo this way. Because what is present is only chromium 3.
Do we still refer to them as cathode anode?
No. As in, cathode anode is just when you set up an electrochemical cell. But what is more important is being cathode and anode means that it's undergoing reduction or oxidation. Yeah. So if I don't choose the term cathode, okay. So here, right, I recognize that I don't have this. I only have this.
Yeah.
Yeah. So it can go this way for this
Only this.
equation. Yeah.
And then the other one is only the
Yeah.
other way.
No, okay. This one, right? Iodine only this is present, so iodine, if you look at the half equations, is only on the left side. So which means that it can only go forward. Yeah. So it will be reduction process.
So we don't necessarily look at the higher inert value.
No. Okay, that's why the thinking process becomes different when you are working with half cell. Half cell is you choose the one with the more positive inert to be the cathode, to be undergoing reduction. Yeah, but this one you have to choose what is available first.
Oh, then we see which is more positive.
Then if this one die can only undergo reduction, then the other party must be oxidized in order for it to work. Yeah.
Must you write it like that, or must it be on the same side?
Oxidized?
You write it like that, then you flip it.
No, because here is by default standard electrode potential, so you should write it all reduction processes. Yeah. So that's why you put a negative sign in front to reverse the sign. Yeah. So this negative sign, right, is to reverse it. If not, we will have use of plus.
What happens if like both reduction and oxidation are possible for both?
Possible. Oh, you choose the one that is more positive. So for example, your team can be on the left side as well as the right side, right? Yeah. So between these two, this one is more positive. So it's more hydrogen peroxide has a higher tendency to undergo reduction. So this means that the team 2 plus have no choice but to undergo oxidation. Yeah. This is how we choose that. Yeah. If you're confused, must ask, because later on when you do your tutorial, you have to practice the same thinking skill. Huh? First of all, you must look for iodine, because iodine, if you look through the half equation, right, iodine is only found on the left side. Yeah, so since it's only found on the left side, then it can only undergo reduction. So anything that's on the left will be reduced, anything that's on the right will be oxidized. Yeah.
Then what if there's like there's both?
Yeah, then you have to choose the one that is more positive as the more likely to take place, greater tendency to take place. Understand? Yeah. So we always, if there's multiple choice, as in there's more than one possibility, we always choose the one that's more positive to take place. Okay, are you done?
There's another equation with iodine on this side.
On the other side, you mean?
Sorry, on the left side.
It's always on the left side.
But it has a higher this one. Then we choose the higher one instead.
Yeah, correct. Okay, so can I go through the answer, or you still working on it? Or you want to check with your neighbor first? You can discuss with your neighbor first. See whether you come to the same conclusion. Are you following?
doesn't agree.
Oh, because you see, when this is reacted away, but is supplemented by this. Because this is the anode, right? Hydroxide is being used up. But then the anode also, the cathode also produces hydroxide. So there's a replacement. Huh? It's aqueous medium. Aqueous medium, all potassium salts are fully soluble. Where got react? What react? You mean precipitation? No, it doesn't precipitate. It's a group 1 metal salt. Okay, so can I go through the answer? Are you ready? So let's look at this. So what are the half equations? So this one is a bit trickier because tin 2 plus can appear on the left side as well as on the right side, right? Some of you actually observe that. So what we need to do now is, when we choose the half equations for the reduction process, okay, do recognize that the reduction of hydrogen peroxide versus reduction of tin 2 plus is a more positive E0 value. Right, so this, by observing that, you should recognize that hydrogen peroxide has a higher tendency to be reduced. Okay, so this means that this will not take place. This is not the preferred pathway. Okay, so if we can zoom in on that already, hydrogen peroxide must be reduced. This means that my tin must be oxidized. So if my tin were to be oxidized, where should I look for my tin? On the right side. Yeah, so the right side will be here. Oh, wrong. Okay, so this one is the right side. Now, you can quote this or you can don't quote this, up to you. Okay, so if you recognize that hydrogen peroxide is the one undergoing reduction, then you must look for tin on the right side. And this is how it will look like. Okay, you are not allowed to flip the equation because by default, E0 value is electropotential reduction process. Okay, so this E0 is by default reduction potential. Okay, so you cannot flip this equation, but you can flip it when you derive the overall equation. Okay, so this is what is going to happen. And when you calculate the E cell, it's more than 0. Okay, so appreciate that. The negative sign here is to flip the value. Okay. The negative sign in front of your oxidation process is to flip the value. Because it's going the reverse way, what? Oxidation. But the E0 is reduction. Yeah. So the negative sign is there to flip it. No, hydrogen, there's also a hydrogen peroxide on the right side. Yeah, there is. This one. There is. Yeah. So never see, then yeah. Okay, so this is how the overall equation will look like. Okay. Do you need me to explain anything else? Anything that is confusing? Okay, sorry. Yeah, so when I use the term E0, is by default reduction. Yeah. Okay, notice that we don't use the term E-ox. Yeah, I know that in JH you're taught the term E0 OX, is it? Something like that. Okay, no longer acceptable, so must change. Okay. Yeah, it's also very confusing to me. Yeah. Okay, so let's look at question number 2. Electrons are released to the external circuit from the cadmium electrode. So is this piece of information important? What's the significance of this piece of information? What's the significance? Cadmium is the anode, all right? Because it's the source of electron, right? Electron is released. So being the source of electron, it must be the anode. Okay, so anode means that it must go oxidation, undergo oxidation. So this will be the cathode undergoing reduction. Okay, so if you look at statement number 1, apple, the amount of cadmium decreases as current is drawn. So is that true? You're supposed to choose statement that is false. So is this a true statement? Yeah, so this is a true statement, therefore not the answer. True. Therefore not answer. Okay, so cadmium is a negative electrode. Is that true? Yeah, it's true. So therefore not the answer. Okay, yeah, you know that it's negative, right? Because it's the one giving out the electrons, therefore negative electrode. Okay, so part C, statement C, concentration of KOH decreases. So that is not true. It should stay constant. Okay, do you know why it stays constant? Because if you look at the two equations, right, this one have to be multiplied by 2. Okay, so as your cadmium undergo oxidation, 2 moles of OH minus will be used up. But at the same time, at the cathode, right, 2 moles of OH minus will be formed as well. Yeah, so for the anode, 2 hydroxide used up. For the cathode, 2 hydroxide will be produced. So used up and being replaced. Therefore, the concentration of KOH remains constant. Okay, that's one way of looking at it. Another way is you add up the 2 half equation. You notice that in the overall equation, hydroxide is not involved in the reaction. So therefore, since it's not involved, its concentration should remain unchanged. There are 2 ways. Okay, you can derive the overall equation, and from the overall equation, appreciate that hydroxide is not the reactant, not the product. Okay, so it's a spectator ion. Being the spectator ion, concentration unchanged. Okay, so that's the second method of looking at it. Then part D, EMF. Are you okay with this? This is true, All right, so therefore not the answer. Yep. Okay, let's move on to the next part. All right, so this is the delta G lah. Okay, so this delta G, you have to memorize. This equation is not provided in the data booklet. You have to memorize. Okay, so it will be delta G equals to negative. It's a negative sign. That's why for delta G, for spontaneous reaction, delta G must be less than 0. For spontaneous reaction, E cell must be more than 0. Okay, so the difference in sign is due to this negative sign over here. Okay, for spontaneous reaction. And please take note, the N over here, the letter N over here, it is the number of electrons transferred, okay, during the redox reaction per mole of written equation. Right, so there should be a written equation for reference for you to deduce the number of electrons transferred. Okay, and the next thing I want you to pay attention to is, please take note when you equate delta G to negative NFE, the units by default is joule per mole. Okay, so when you calculate delta G from this negative NFE, right, the units by default is joule per mole. It's not kilojoule per mole, it's joule per mole. Okay, so this for example, you can look at it at your own time. Okay, do you need me to explain anything? All right, you look at this, then you work on the next checkpoint. Okay, I'll give you, yep, a lot of checkpoints to do. Yes.
We use this equation rather than this one.
Mm-hmm. Oh, because notice that your team right happen to appear on both sides of the half equation. So there's one half equation whereby team is on the left side. Yeah, then this one is also on the left side. So when both on the left side, we are considering them as undergoing reduction process. But when I quote that two values, right, this one is the more positive one. So in other words, between team 2 plus and hydrogen peroxide is the one that has a higher tendency to undergo reduction. Okay, so this is the one that we chose over the other team 2 plus. So if this is reduction, then the other one must be oxidation. Yeah, so team 2 plus must be appearing on the right side, in other words.
When do we consider this case? Because both of them also offer a positive for the then
Yeah, so in this case, remember I said that they must appear on the opposite side. But now both of the reactants are appearing on the same side. So having both reactants appearing on the same side means left side, in this case, they can only undergo reduction. Yeah, so there's no source of electron. There must be the source of electron. So where does the electron come from? Nowhere. Yeah, so no reaction. So the criteria is they must appear on the opposite side. Opposite side. Just so that one is reduction, the other one is oxidized.
What if it's this one you times 5?
Yeah.
This one times 2. And one is this one
This
2,
per mole of return equation. This is the return equation. Yeah. So the number of electron transfer per mole of return equation. So how many moles of electron transfer? Yeah. 10.
So 5 or 10?
Hmm?
5 or 10?
10 per mole of return equation.
don't know in the unit.
Huh?
There's the C not in the unit.
Why is C not a unit? Faraday's constant. This one is energy per charge, right? No, man? E naught. Electromotive force. What is is voltage, right? Voltage is joule per charge. Oh, just not there. Ask your physics teacher. Oh, voltage. Yeah, I thought voltage is a measurement of energy per charge. Right? Oh, yeah. Energy per charge, ma? It has. A physics student, no. Yeah, lor. See, I still remember my physics. What's wrong? Huh? Power equals to VI? Oh, can I go through the answer? Are you ready? Okay, we'll discuss the physics later on. Okay, so let's look at this. So delta G is per mole of written equation. So the delta G of this reaction involving 5 moles of ethane dioxide acid and 2 moles of manganate is a negative 1940 kilojoule per mole. All right. So remember, first thing to do is to convert this to joule per mole. Remember, I said that before. In this equation, the units for delta G must be joule per mole. So you will be negative 1940 times 10 power 3. Convert to joule per mole first. Okay, then it will be equals to your negative n. So what is n? How many number of electrons transferred per mole of written equation? 10 electrons. So 10 of them. Are you able to see that there's 10 electron transferred? Don't say 10 here, 10 here, 20. Okay, 10 electron transferred. Okay, understand me? 10 here transferred to 10 here. Yeah, so 10. Then your Faraday's constant 96500. This one you learn in physics also, right? Yeah, is yes or no? Oh, you don't learn it? Huh? Okay. You don't? You don't learn electrolysis, right? Huh? Okay. So this value is found in your data booklet. This value is found in your data booklet 96500. Okay, then your E cell, E naught cell. So this is you are supposed to find. Okay, question mark. All right. So since you know your delta G value, since you know your delta G value, then you can calculate. So what is your E naught cell? What do you calculate your E naught cell to be? 2.01 volt, is it? Okay, so do you have this? Do you have this or not? Have, okay, so after you have applied this, after you have obtained your E naught cell, what's the next thing you are supposed to do? Is this the answer wanted? No, you are supposed to calculate the E naught for your reduction process of carbon dioxide to ethane dioic acid. Okay, so how do we do that? So first of all, you have to identify the reduction half. Okay, so obviously the reduction half is involving your manganate. Yeah, so remember, manganate is reduced to Mn2 plus only. In highly acidified medium, you should choose the manganate reduced to Mn2 plus only. Okay, so this will be the E naught value. Okay, then how do you, so do recognize that this is your anode. This is your anode reaction. So anode reaction will be as such. So you have to calculate the E naught value. Okay, so you have to apply this. E naught cell is equals to your cathode minus the anode, right? So it will be plus 1.52 minus the E naught of your ethane dioic acid. Oh, sorry. Carbon dioxide to ethane dioic acid. Okay, then this is the positive 2.01. Okay, then you just rearrange the equation, you should be able to get the answer. Huh? Yeah, so what's your answer? Plus 3.53? No. Minus 0.43. Minus or plus? Minus. Minus, right? Huh? 49. Okay, 49. Did you manage to get this? Yeah. Okay, so we are done here. Lah. So let's look at the limitations of using standard cell potentials to predict spontaneity. All right, so number one, please take note, E0 value is not a prediction of rate. So you can have a very spontaneous reaction, but it can take place very slowly, high EA. All right, so E0 cell is a spontaneity, just like a delta G. So E0 cell measures the tendency, like a delta G measures the tendency, but has no relation to rate. Please take note. Okay, so doesn't mean that rate will be very fast, huh? Okay, that's one thing. And also number two, under lab condition, if we are doing reactions in the lab, right, there's no way we can follow the standard condition. All right, so even though we can calculate E0 values to make a prediction, but it doesn't mean that it will definitely take place because under lab condition, it's not standard. Okay, so what you predict using E0 may not be accurate. Okay, so that's the second limitation. Okay, this one is for your information, but this can be given as a question stem for you to apply. All right, so even though it's not exactly in your syllabus, but it can be given as a question stem in A-level question for you to apply your formula. Yeah, so you just substitute into the formula. We will explain to you. Okay, so applications of electrochemical cell, the fuel cell. Okay, so we are not going to cover the conventional batteries. Does physics covers also the conventional batteries? Okay, okay, yeah. I mean, maybe to some of you it's very interesting, but it's not very interesting. Okay, so anyways, to me it's not very interesting. Okay, so this one is you can read on your own. The other one is the fuel cell. Okay, so the fuel cell, I will go through it the next time I see you. Okay, so with this, for today's lesson, you should be able to do your tutorial already. So refer to the Excel sheet on what are the question numbers that you need to complete. Okay, for you to prepare for next week's tutorial. Okay? Yeah. Fuel cell is in your syllabus. The conventional one are not in your syllabus. Because fuel cell is a sustainable energy source. Sustainable. Yeah. Okay, so you need to study that.